Lieutenant Colonel Robert W. Fett, Headquarters, Air Weather Service.
Only a glance at Air Force history tells us that year by year we fly higher, faster, and farther. There was a time when all a pilot had to know about weather were the local conditions in his area. Today, weather conditions on the other side of the world can be just as important to a pilot and navigator as the weather they experience at takeoff. Global weather information over great areas is constantly supplied by satellite meteorological photography, but it is useless unless those still photographs are accurately interpreted by our Air Force meteorologists. To enhance the general understanding of this satellite photography, the Air Force presents this seminar on upper air and tropical synoptic application, based to a large extent on material and techniques developed by the National Environmental Satellite Service. The Air Force meteorologists are Major Jerome Ashman and Mr. Arthur Smith of the Environmental Technical Application Center, Air Weather Service, Military Airlift Command.
First, a word about satellite meteorology. We want to emphasize that satellite meteorology is not the solution to all the problems confronting the meteorologist, but is another tool in our trade. It must be used in conjunction with worldwide synoptic data. It is not a substitute for surface observations, but it certainly does give us an overall picture that aids us in the analysis of worldwide weather. In remote areas, it is frequently the first and only tool to identify severe or unusual weather. One of the cloud patterns we see frequently in satellite photographs is the spiral-shaped vortex. Vortices are easily identified in cloud photographs. The main point to emphasize with respect to vortices is that when we see dry air spiraling around a vortex reaching into the northwest quadrant, we can say that the storm has reached maturity. We can now forecast the filling of the surface low. This slide gives us an example of a mature vortex. The dry air has spiraled completely around the low. You will remember that one of the points we must emphasize is that we must identify the level of the clouds we see. This will aid us in determining the flow at that level. For example, if we look at the anvil cirrus in this picture of weather east of Florida, we can see the cloud pattern describing a cyclonic circulation. Being anvil cirrus, their tops are at approximately the 250 millibar level. We speak of high, middle, and low cloud families. Now let's look at middle clouds and examine the flow pattern at 500 millibars. Art?
From our textbooks, we know that we have divergence at approximately 500 millibars between a trough and the next ridge downstream. This will result in net upward vertical motion in this area. Here between the ridge and trough, we have a region of net downward motion. These regions of upward and downward motion are reflected in the cloud patterns. They allow us to locate the ridges and troughs at approximately 500 millibars. In the region of upward motion, a funnel cloud band will be well organized, while in the area of downward motion, the funnel clouds will be weak and or diffuse. A trough line at 500 millibars can be positioned from the center of the vortex, just to the rear of any vorticity maximum in an open cellular field, to where the funnel band weakens. Ideally, the 500 millibar ridgeline is located along the leading edge of the multi-layered funnel cloud band. This is dependent upon the degree of curvature in the ridge, or in other words, With a sharp ridge, the clouds will terminate very close to the 500 millibar ridgeline. With a broad ridge, the multi-layered clouds will extend downstream a few degrees beyond the ridgeline. In this satellite picture, we can see the frontal cloud band. These clouds are strongest between the trough line here and the ridge line here. This next slide shows a ridge line where the middle clouds terminate abruptly. And in this slide, we have a picture of the 500 millibar trough being located where the middle clouds of the frontal band weaken, down in this area. Another use of defining the 500 millibar flow can be seen on the next two slides. First, we have here the typical cloud pattern associated with zonal flow. A cloud band with great east-west extent and a small north-south extent. Now, when we have sharp troughs and ridges, we have cloud bands with little east-west extent and a great north-south extent. The clouds, of course, being in the region of upward vertical motion between the trough and the ridge. This slide is a good one for summarizing the flow pattern at 500 millibars. From the middle clouds, we can identify a ridge line here, a trough line here, another ridge here, a final trough here, and another ridge line out here. Jerry?
We've been talking about low and middle level cloud patterns. High level clouds are particularly important to us today because of the indications they give us of the upper air flow and because so many Air Force missions are flown near the cirrus level. Identification of a polar jet stream is